Welcome to another day where I'm going to move slowly through an idea I think is extremely important. I didn't want to rush through it last week, and I do not mind if that is all I am able to tell you today. I want to ask the following questions. Is the identity transformation of a sum equal to the sum of the identity transformations? That is, if you have two things, if you have two vectors, V plus W, that's a sum. If you do an identity transformation of V and you do an identity transformation of W, and then you do an identity transformation of the sum, are you going to get the same answer? Is the identity transformation of the sum equal to the sum of the identity transformations? Is the identity transformation of a scalar multiple equal to the scalar multiple of the identity transformations? Is the identity transformation of a weighted sum equal to the weighted sum of the identity transformations? If the answer to all this is right, then that shows that the identity transformation is a linear transformation. If in addition, the identity transformation is a transformation of vector to vector, then it is now a tensor. I will repeat that. Please pay attention. I want to repeat what I've said. The three questions I'm asking, they are on the screen. If those three questions answer to the affirmative, the conclusion is that the identity transformation is a linear transformation. So when you say something is linear, it means it obeys these three rules. When anything is like this, then it's a linear transformation. Any transformation that obeys these three rules, the second and the third rule are the same. Actually, the second rule is subsumed in the third. So they are, in fact, the last one contains the previous two. The identity transformation of a weighted sum, is it equal to the weighted sum of the identity transformations? If that is true, then the other two are true. Then it shows that the identity transformation is a linear transformation. If in addition to being a linear transformation, the identity transforms a vector to a vector, then it is a tensor. A tensor is something that, first of all, transforms a vector to a vector and does it linearly. So once that is understood deeply, most of the issues are a matter of working it out. That is all you really need to understand. That before we call a transformation a tensor, it must be something transforming a vector to a vector. If it does that, and it does it linearly, then it is a tensor. Now, when we say tensor, we mean a second order tensor. If I say tensor without any adjective, without any qualification, I am talking about a second order tensor. If I'm talking about any other tensor, I will put the correct adjective to remind you. So if I want to talk about a third order tensor, I will tell you I'm dealing with a third order tensor. If it's fourth order, I will say it's fourth order, fifth order, sixth order, whatever order I will say. But if I do not specify, then I'm talking about a second order tensor, because the word tensor without any qualifications refers to the second order tensor. Before I now go on and demonstrate this in several cases, I want to see if there's anybody who doesn't understand that, because we are going to be repeating this idea over and over. Can I have anybody who has a question to ask on this particular issue? Because I'm going to say it again, and we are going to have proofs of. We are going to now carry the same thought through 7 different definitions of transformations, or through 7 different transformations. Any question from anyone? If you have no question, do you mean that what I've said is clear to the class? It's clear to everybody? Please, I'm waiting at the chat room. I'm looking at the chat to see whether what I've said is clear or if there's any question. Okay, it's clear. Oluwatobi, you say it's clear. Anybody else wants to comment? Liberally comment. I hope you remember that I pay you for commenting with marks. So if you, because we count all these things at the end, so better comment now when you have the opportunity. Okay, so we start with the annihilator transformation. We represent the annihilator transformation by the big symbol O. Its characteristic may at first look may appear trivial. It turns every vector it transforms to a zero vector. So any vector is a zero vector, no matter what the vector is. Mathematically, we can write it that for any U that is a vector, when we say something belongs to E, which is the Euclidean vector space, we mean the thing is a vector that can do inner product. So what defines it is that OU is equal to the vector 0. The vector 0 is not the same thing as the tensor 0. The tensor 0 is the big O, which can operate on U. The vector 0 cannot operate on U without qualifications. It can take a dot product, it can take a cross product, it can also multiply by a scalar, and it can be part of a vector or tensor product. But when you see a vector operating on something operating on a vector, that thing is a tensor that we can treat like that. So we distinguish between the big O and the small o. You cannot use the big O when the small o is expected, neither can you use the small o when the big O is expected. So this defines. So we are now going to answer our questions. If you have a sum, OU plus V is the annihilator operating on U and operating on V separately, is it going to give you the same result when the annihilator operates on the sum? If you do that to a weighted sum, are you going to get the same result? That is a question we are going to keep asking. Okay, so the spherical transformation. This is the definition of the spherical transformation. For any vector U, or the U that is a member of the Euclidean vector space, the identity transformation I is given by and there, if we are given U and we are given the identity transformation I, and we are given a real number gamma. Gamma can be any real number, can be a fraction, can be positive, can be negative, but it is a real number. We represent the spherical transformation with the big S as defined by gamma IU. It's just a scalar multiplied by the identity transformation, so that S is equal to gamma I. What answers do we have for the familiar question when we ask them about the spherical transformation? Is the spherical transformation of a sum equal to the sum of the spherical transformations of the individual members of the sum? Is the spherical transformation of a weighted sum equal to the weighted sum of the individual spherical transformation? So that's the question we ask. If the answer is yes, then it means that the spherical transformation is linear. If I want to confuse you in an objective test, I would answer all those questions in the affirmative, and one of the answers would be, it shows that the thing is a tensor, and that would be wrong. It will only be a tensor if, in addition to the linearity, it transforms vectors to vectors. So if it doesn't transform vectors to vectors, even if it is linear, it is still not a tensor. So something that transforms linearly is only a tensor if what it transforms linearly is a vector. If the answer to all the questions asked above, if the answer is, in each case, that the transformation of a sum is the sum of the individual transformations, that the transformation of a scalar multiple is a scalar multiple of the transformation of the initial vector, and that the transformation of a weighted sum is the weighted sum of the constituent vectors with the same weights, then we can conclude we are dealing with tensors, because what is being transformed here are vectors. We are concluding we are dealing with tensors because we are transforming vectors linearly. Anything that transforms vectors linearly is a tensor. The transformations we have discussed are all linear transformations, and they are therefore tensors. This definition that I am emphasizing and repeating until you are bored with me, I don't care if you get bored, because that means you will remember that I talk about it too much. Why am I talking about it too much? Because it is going to just keep recurring and recurring and recurring and recurring ad nauseum. And if you don't know it now, you are going to pay over and over and over and over for not knowing. So it's better you settle down and understand it right away. So we will now go and establish the tensor character of 7 different transformations. 1 is the projection, 2 is the coordinate transformation, 3 is the dyad, then the identity, the annihilator, the spherical, and the vector cross. We are going to now demonstrate their tensor character. These are all transformations. When you want to evaluate their, demonstrate their tensor character, what will we be trying to do? Please go to the chat room and tell me, if I want to establish the tensor character of these things, what will I be trying to do? How will I be able to establish their tensor character? What will I do that will make me establish their tensor character? Anybody? I want to establish tensor character of 7 things. For each of them, what am I trying to do? Yes, Ajibola Matthew, you got it right, but I want you to repeat yourself and state it as 2 things. You have mixed everything up into one thing. I want to be analytical. What will I be trying to do? There are 2 things I will be trying to do. You got it right, Ajibola, but you got it as a single thing. I want it in 2 different points. What will I be trying to do if I want to establish that these things are tensors? Prove that the operation satisfies the 3 conditions. Potentially transform, okay. Testing the transform, if the transform vector and if the transformation is linear. Yes. Okay, Chuku states it the way I want it stated. We are going to check. First of all, does it transform linearly? And does it transform vectors linearly? If we can show that it transforms vectors and it transforms them linearly, then we have proved that what we are dealing with is a tensor. So that's all I'm going to do. I will take them one by one. I will check how it transforms. If it transforms linearly if vector is transforms linearly, then what we are dealing with is a tensor. You may be bored, but if you are bored, just remember those steps. And remember that actually we established the linearity. So you need to know, how do you establish linearity? How do you establish linearity? Anything that transforms a weighted sum as the weighted sum of the individual elements is linear. If I transform a weighted sum, and it is the same thing as if I transform them individually and do a weighted sum on the result, then if the results are the same, it doesn't matter whether I transform first before doing the weighted sum, or I do the weighted sum before doing the transformation. If I get the same answer in either way, then the transformation is linear. You do a weighted sum first and transform, or you transform first and do a weighted sum. If you get the same answer in both cases using the same weighted sum coefficients, if that is it, then the transformation is linear. That's how you define, that's the definition of a linear transformation. You want to do a linear transformation, you do a weighted sum before you transform. Then transform first and do a weighted sum. If you get the same answer in both cases, then what you have is a linear transformation. If what you are actually transforming are vectors, then what you have is not just a linear transformation, it is a tensor transformation. So Ogochukwu, thank you for that. Okay, so we are now going to take a look at the identity, the annihilator, and the spherical transformations. These are simply two special cases of the spherical, because in the case of the spherical, if gamma is 0, you have the annihilator tensor. If gamma is 1, you have the identity tensor. If gamma is arbitrary, you have the spherical tensor. So all the three are exactly a part of the same idea. It is easy to see. So its linearity from that of the identity. We therefore begin by establishing this. Okay, let us first of all establish the linearity of the identity. Okay, I will go back to the other one. We'll see. Now, identity tensor, if you transform a sum, is equal to U. If you transform U plus V with identity transform, is equal to U plus V. Is that obvious to everybody? Because remember, identity transform does nothing. So if you apply it to U plus V, which is a vector, you can call it W. That means that it's W you will get at the end by the definition of the vector space, and it's also a vector. Consequently, if you transform U, you get U. You transform V, you get V. If you transform U plus V, you get U plus V. Now, so here, so far, so good. But this equality is coming from the nature of the identity itself. U and IU are the same. V and IV are the same. So U plus V is the same thing as IU plus IV. The identity operation distributes linearly over addition. The scalar multiple of a vector is also a vector. So I of alpha U is equal to alpha U is equal to alpha IU. And I of beta V is equal to that. So because the linear combination of vector is also a vector, therefore, I alpha U plus beta V is the same thing as this, which is the same thing as I into alpha U plus I into beta V, since I does nothing. So this and this are equal. So it's clear that the identity transformation transforms linearly, because this beginning, that is we do the linear sum. We do the weighted sum before transforming. Here, we transform individually first, and we do the weighted sum of the results. If these two are equal, then the transformation is linear. If what they are transforming is vectors, then it shows that the identity is actually a linear transformation of vectors, and therefore it is a tensor. So we can come back to the spherical here. Now, given U and V are vectors, alpha, beta, and gamma are real numbers, and I is the identity tensor. We test the transformation SU is equal to gamma IU. If we do that, we can even conclude immediately that if I has already been demonstrated to be a tensor, then gamma I is obviously a tensor. Multiplying it by scalar doesn't change the tensor character of it. So in this case, we can have S of alpha U plus beta V, and we can all these equalities have reasons. And what is the reason for the first one? The first equality, the reason is that by definition, S is equal to gamma I. So all we just did is to substitute gamma I for S. That is the reason for this equality. For the second equality, okay, what is the reason for the second equality? What is the reason for this equality on the second line? The first line is equal because we're just substituting S for gamma I. What about the second line? Why is it true? Because the identity tensor gives identity tensor, yes, identity tensor changes nothing. So the identity tensor operating on alpha U plus beta V is the same thing as alpha U plus beta V. That is the reason for the second line. What is the reason for the third line? Yes, a simple scalar multiplication. In a simple multiplication, gamma will be distributed over will dominate the plus. So that's the thing. What's the reason for the fourth line? Fourth line. Okay, so the identity tensor comes in again, which it doesn't change anything. Now, why is the fifth line true? Why is the last line true? Yes, that is Oluwatomiwa Ekunife, substitution, James Udoma. Good. So, okay, so each equality here has a reason. Each equality has a reason. That's the important thing. This is the reason why I didn't want to rush through. I knew I was getting tired. I guess you might have been getting tired last week. That's why I wanted us to use a fresh mind to look at this. It looks so trivial, but it is not. But look at the conclusion we are making now. If you take the first line, the left-hand side, and you take the right-hand side of the last line, see what we are saying. What we are saying here is that if you do the weighted sum first before you do the transform, it's the same thing as when you do the transforms first and you put a weighted sum. And that shows linearity. It shows linearity, and because what we are transforming are vectors, it shows that we are dealing with a tensor. So we have proved there that the spherical tensor is, the spherical transformation is linear and therefore a tensor. So it contains the annihilator and also contains the identity, though it is a circular argument because it was identity that was very useful in establishing this. So we have established that the spherical tensor is, the first spherical transformation is a tensor, the identity transformation is a tensor, and the annihilator transformation. Now, if you just put gamma to be 0, proves that the annihilator tensor is a tensor transformation also. So we were trying to see what happens to 7 different things. We have now been able to check 3 out of them: the identity, the annihilator, and the spherical. It now remains the projection, the coordinate transformation, the dyad, and the vector cross. So those are the things remaining for us to now check. So we have done this. So we have done the identity. So the next thing we want to do now, we want to look at the dyad. We knew the dyad since last time. We got familiar with the dyad last time. And by definition, if given A and B that are A, B, and V that are vectors, the dyad A circle times B is defined by the transformation equation. That is, when it operates on V, it transforms it to A multiplied by the scalar, which is the scalar product of B and V. That is what defines the dyad. So that is the definition of the dyad. So that the input operand, V, is a vector, and the output operand is also a vector, but it is now directed along the first vector in the dyad. So all it does is changes the direction of the vector, but it's still a vector that you get. So anytime a dyad transforms a vector, all it does is that it changes the director and magnitude of the vector. The vector's magnitude is altered, and the vector's direction is also altered. So it changes the vector, but it still produces another vector. The tensor credentials of this can be found if we find how the dyad transforms alpha u plus beta v, where alpha and beta are real numbers. We observe that the weighted sum alpha u plus beta v is a vector. Does the dyad transform it to a vector? How does the output vector relate to the input? If it transforms a vector to another vector, and then we want to know whether the transformation is linear. That's what we are going to check. Okay, so apply the transformation to the weighted sum. Again, be ready, class, to answer me quickly so that we move fast. Why is the first equality here correct? The first line, why is it correct? Yes, David Anigbo got it right. That is the definition of the dyad. David Anigbo, the first line is the definition of the dyad. That is, if you have a dyad, you take the dot product with the vector you are operating on is this weighted sum. So that is why the first line is correct. That's the definition of a dyad. The answer that was given me earlier on by who now? The answer that was given me by Ogochukwu, is it Ogochukwu? Yes, Ogochukwu Uba, that the dot product is distributive. That answer applies to the second line. That answer applies to it because the dot product, just like any other product, is distributive over addition. So, why is the third line correct? Okay, this way property of vectors, that's correct. And now, why is the last line correct? How can we conclude the last line from the third line? Okay, the definition of the dyad. That is coming from the definition of the dyad. But if you now look at the last line and you compare it to the first line on the left-hand side, if you compare it to the left, you can see now that you first of all took the weighted sum of U and V before you operate the dyad on it. But here, you operated the dyad on U, operated the dyad on V, and took the weighted sum of the result. If those two are equal, it shows that this transformation is linear, showing that the dyad of a weighted sum is the weighted sum of the individual dyads. Therefore, the dyad is a linear transformation and it transforms a vector to a vector. It is therefore a tensor. So out of the 7 things we started with, we have now showed that 4 are tensors. The annihilator is a tensor, the identity is a tensor, the spherical tensor is a tensor, and the dyad is also a tensor. We are left with 3. The 3 we are left with are projection, coordinate transformation, and vector cross. So let us see how we get through those 3. Before we go into proving the tensor characteristics of the projection transformation, let me put it to you the way lawyers will put it to you in a court of law. I want to put it to you that when you talk about a projection, it can be a scalar. You talk about a projection, it can be a vector. You talk about the projection, it can be a tensor. And it is important for us to know which one we are referring to. So there is a projection scalar, there is a projection vector, and there is a projection tensor. And so I will define the projection transformation, which we will prove to be a tensor now. Then I will show you that there are projection vectors, projection scalars, and they are in addition to the projection tensor. We introduced the shadow transformation as if there were parallel rays of light creating the transformation where it happens. When this happens, it's called a projection. In order to establish its tensor credentials, we shall regenerate this same situation mathematically and introduce the projection transformation. Given X and V, which are vectors, the transformation Px, which is defined as 1 over the modulus of x squared into the dyad of x on itself, transforms every vector V to a shadow parallel to x. Because if you operate V on it, by the definition of dyad, you know what is happening. 1 over modulus of x squared is a scalar because the magnitude of a vector is a scalar. Squaring it is still a scalar. So you forget about that and just carry it along. But x circle times xv is the same as x operating on v dot scalarly in the direction of x. That is the definition of this dyad here. So if x and v are perpendicular, the transformation stimulates the midday overhead sun, casting our shadow on our feet, which means that because at that point, x dot v is 0. So everything now becomes 0. This is the definition. What we have done on page 30 is that we have showed the definition of the projection transformation on our way to proving that it is a projection tensor. 1, let us say V is a vector and X is another vector, and the two vectors are oriented. Okay, so let us say we have vector V and vector X. They have two vectors directed in such a way that alpha is the angle between them. If I drop a perpendicular line from the tip of V onto X, I have this crossing here. Does the class agree with me that V sine alpha is the value of this length? Is this length here? You can see that V sine alpha is this length. If V sine alpha is this length, now, what is this quantity? I want to write what I think that quantity is. You'll be telling me, you'll be thinking of that quantity. I want to say that this quantity is the same thing as something I want to do here. Yes, I am claiming that this quantity is the same thing as V dot X over the modulus of X. This scalar quantity we have here, that is V dot X over the modulus of X. Let me see what the class thinks. I'm talking of the mathematical calculation. Do you agree with me that V sine alpha, oh sorry, not sine, it's cos. That's an error there. V cos alpha. Is V cosine alpha. This, first of all, do you agree that this projection, the length of the yellow line is V cos alpha, which is the same thing as V dot X divided by the modulus of X? If you do not agree immediately, just compute this and you see whether you will get this. This quantity you have here is the projection scalar, because it is the magnitude of this. It is what you are talking about now is the magnitude of the yellow arrow. So the projection scalar of V upon the X direction is the scalar V dot X divided by the modulus of X. Now, if I multiply that, what is the direction of this? What is I, which is the direction of this vector? You see, if you want to now talk about the vector, not just its magnitude, then you have to put the direction. That's the unit vector on this line. Do you agree with me that I there? Do you agree that the unit vector along this direction is simply X divided by the module of X? So that if I change, I can therefore say that this is equal to this. So what we are saying here is that the projection scalar is V cos alpha. If you now append the direction vector to make the whole thing a vector, this is what you got. And if you look at this quantity very well, you'll see that that is exactly what the projection vector is bringing out. So you can see that 1 over the mod of X squared is coming out from this two. This V dot X is the same thing as X mod of V with this X outside. So that means that when you apply the projection vector on any vector, it transforms that vector to the projection vector. You have the projection transformation, you apply it to V, it gives you the projection vector along the direction of X. And if you want to look at the projection scalar, which is the magnitude of it, is simply V cos alpha. So whenever we see the projection transformation, let us realize that whenever it operates on a vector, it is going to give us the projection vector. And the magnitude of that projection vector is the projection scalar, and this thing is the projection transformation. So what are we going to do next? We now want to prove that the projection transformation is actually a linear transformation of vector to vector, and therefore is a tensor. Now, I have proved it here, but I don't want to waste my time even proving it again. I have already proved that a dyad transforms a vector to a vector. I've proved that a dyad transforms a vector to a vector. So if what you have as a projection is simply a scalar multiplied by a dyad, it will also transform a vector to a vector, because what you have in the projection vector, a tensor, is just a scalar multiple of a dyad. If a dyad, whatever a dyad does, then a scalar multiple of it will do similar things. If a dyad transforms linearly, a scalar multiple will transform linearly. If a dyad transforms vector to vector, the scalar multiple will also transform vector to vector, because multiplying a vector by a scalar still doesn't change it from being a vector. So multiplying a linear equation by a scalar does not change anything. A linear equation remains linear whether you multiply it by a scalar or not. So that is enough. The fact that the dyad transformation is linear already makes the projection transformation linear. What have we learned in the process? In the process, we have learned that there's a projection scalar and there's a projection vector. Here, the quantity v cos alpha, which we prove to be equal to v dot x over the mod of x. This v cos alpha is simply v dot x over the mod of x, is the projection scalar. And when you append the unit vector to it, you get the projection vector. And that unit vector is simply x over the mod of x. If you bring this thing together, you will see that it's essentially the same thing that you have when the projection vector operates, a tensor operates on any vector. That is the quantity you have here. It's the same thing. So even though it is not looking like your familiar v cos alpha, it is not obvious that the cosine of alpha is inside this thing, but it is there because of the definition of the dot product. So the dot product gives you the magnitude of x plus times the magnitude of v, cosine of the angle between them. And one of the magnitudes will cancel this one out to make it correct. So I decided I don't want to go through this, but you can go through this and see that at the end of the day, when you apply the projection to a weighted sum, you take the weighted sum first, you apply the projection. It's the same thing as if you take the projection in each case and you now apply the weighted sum to the answers. So, and if that is the case, that means that the projection transformation is a linear transformation of vectors, and consequently, it is a tensor transformation. The linearity of the dyad induces linearity to the projection tensor. So we do not need to worry ourselves. If somebody asks you, why is the projection linear? Of course, you don't even need to go through this proof. The proof that I have here is not necessary because there's linearity in the dyad. Therefore, the projection tensor, the projection transformation is linear, and therefore it is a tensor. So let's see, how far are we gone? What do we have left? We have shown that the projection is a tensor, dyad, identity, and a elector and spherical. So we are now left with the coordinate transformation and the vector cross. The coordinate transformation. Given a set of coordinates, you can see the diagram there. Given a set of coordinates with basis vectors E1, E2, and E3, we can transform to the coordinate with basis vectors Xi1, Xi2, and Xi3 with the transformation, which is the dyad Xi circle times EI. We can prove this very easily. Easy to prove. Transform any vector V. If a vector V is referred to the E1, E2, and E3 axis, okay, just take any specific vector 2E1 plus 3E2 minus E3. Now, apply this transformation. You see that when you apply the transformation after you work it out, it is the same thing as 2 Xi plus 3 Xi, 2 Xi1 plus 3 Xi2 minus Xi3. So it is completely transformed to the new coordinate system exactly with the same coefficients. So that is what the coordinate transformation does. If one system is a rotation of the one system is a rotation from the other, then the transformation is a rotation. So that is how. So this quantity here is a coordinate transformation. It's a coordinate transformation from the coordinates E1, E2, E3 to Xi1, Xi2, Xi3. That is what it is. Now, can we prove that the coordinate transformation is a tensor? In a single sentence, can anybody prove it? I want to see whether you heard me or true. If I tell you to prove that this is a tensor, what will you do? Can you prove that this is a tensor? Yes, James, you are right. We test it on a vector and we check whether it is linear, isn't it? Is that not what you are saying? Yes, James, I understand you. But there's an easier way. There's an easier way. James, Ajibola Matthew. We need to show that it transforms to a vector, okay? But there's an easier way. I'm telling the class there's an easier way. I can hear you, but there's an easier way. The easier way is to realize that this is a dyad. It's a dyad. If it's a dyad, we've already proved that a dyad is a tensor. So, if it's anything that is a dyad or sum of dyads, it's already a tensor because the dyad is a tensor. So we don't even need to prove this because we have recognized that it's a dyad. A dyad, a sum of dyads or dyad multiplied by a scalar, they are all tensors. So we don't need the proof. If it has a dyad, it is a tensor. If it's made up, I think if it's made up of dyads, then it's a tensor. So even though I went ahead, how did I prove it? Did I prove it? Yes, I didn't. Okay, yes. I went ahead to prove it here by proving its linearity. But we don't need to do it because the linearity of the dyad induces linearity to the coordinate transformation tensor. So since the dyads are linear, then the coordinate transformation is also linear. But you can prove it from first principles directly here. So whichever way you like, you can do it. So we get to the last one. The last one is the vector cross. This is the definition of the vector cross. And again, the vector cross is a sum of dyads. This is the definition of the vector cross. It's a sum of dyads. And therefore, it is a linear transformation. You want to prove that it's a transformation, it's a tensor, prove that it's transformed vectors to vectors, and that the transformation is linear. But we don't need to. We can just immediately conclude that since it's just the linear sum of dyads, then it's a tensor. A linear sum of dyads is a tensor. But I went ahead, I think, to prove it here. So you can go ahead and see. So I think I've satisfied myself that you get the gist of what is a linear transformation. If you do a sum before transforming, and you transform first, and then do a sum of what you have transformed. If the answer you get in the two methods are the same, and they transform, and since you are transforming our vectors, then you are dealing with a tensor. A tensor is the linear transformation of a vector that produces another vector. Mathematically, given that u and v are vectors, the transformation v is equal to tu is a tensor if it is linear. It's a transformation from one Euclidean vector space to another. Depicting the set of tensors as L, we write that T belongs to L, where L is something that transforms the Euclidean vector space back to itself. It must be a linear transformation. So we can also write it pictorially and say if alpha plus beta, if alpha A plus beta B goes through a linear operation such that the answer is alpha TA plus beta TB. So when that is transforming the whole thing, it seems as transforming it one by one and taking the linear and taking the weighted sum after that. Vector to vector transformations. Every transformation we have seen so far has been shown to be a tensor. This begs the question, Are all vector-to-vector transformations tensors? I think while we are begging that question, I want to give you 10 minutes break. We don't have a lot of time left, but take 10 minutes break and we will conclude the class at, please come back in 12 minutes time. That is a quarter past noon. Come back a quarter past noon and then we'll finish. Admin, please suspend the class for 30 minutes. We've looked at 7 transformations so far, and they have always been tensors. This begs the question, are all vector-to-vector transformations tensors? The answer is no. It is possible to find vector-to-vector transformations that are not tensors. Recall, in order for a transformation to be a tensor, in addition to having operand as an input, output as vectors, the transformation itself must be linear. Example of vector-to-vector transformations, operations that are not tensors, are easily found. Here are some examples. The transformation E1 over the modulus of V. Transform the vector V to this vector that has the inverse of the modulus of V as the value. It is not a tensor transformation. The tensor TV, which is the modulus of V E1, this is equation 2.2, and this is equation 2.3. Well, I decided to do it here to open it up. So let us take a scalar, let us multiply it by a scalar. If you multiply it by a scalar, this is the answer you get. It's 1 over alpha, which is not, because it is not, if it was a tensor, you multiply it by a scalar, it's written as that scalar multiplied by the tensor of itself. But instead, it is 1 over alpha. So because of that, this is a nonlinear transformation. And therefore, this quantity here, a transformation like this is not a tensor transformation because the transformation is not linear. Multiplying by taking the tensor after you have multiplied by a scalar is not the same thing as taking, it's not like multiplying by a scalar and taking the tensor. So that is one example. Another example is TV is equal to V modulus of V E1. This is not a tensor, and the proof that it's not a tensor is that, first of all, when you multiply by a scalar, you have no problem. But when you add the two together, it doesn't give you the transformation, the sum of the transformations. The transformation of the sum is not equal to the sum of the transformations, therefore, it's not linear and hence not a tensor. All tests of linearity must be satisfied for the tensor nature to be true. If it violates one, that's enough. The next one, TV is equal to A dot VE1. It's a tensor transformation. You can check that it satisfies all the conditions here. TV is equal to A cross V, which transforms the vector V to the vector A cross V. It's a tensor transformation. And the A cross itself is the vector cross of A. This is a tensor whose component form is this. It's a transformation of a vector to a vector. Its linearity was established already, so we can look at it again. The things we established there, and because there is because of this dyad here multiplied by a scalar, it's already a tensor because any linear sum of a dyad is a tensor. So, you food for thought. We've already done this first one. The second thing is, the inverse of a tensor, is it a tensor? So just check that out and think about that for next week. There is an interesting, there is a guide here as to which questions you should attempt so far. So, and then I may change this, so let me not emphasize this slide 46 too much. I've not really looked at it again. I want to look at it before. Please ignore slide 46. Let us end the class now. ignore slide 46 because I'm not sure whether it is current, because I've not looked at it for your set. This is what we used the last time I taught this course, so which was 2 years ago. So it may not be appropriate to you.